In this class, we study binomial theorem. So we frequently encounter situations of using binomial theorem in mm, various physics problems. So we prove the binomial expansion, a plus b to the nth power is a sum expressed in this form. We find that there is a polynomial in a and b. The sum of the powers is the same. K plus n minus k is always fixed to be n, that is this power, and there is a coefficient that is called the binomial coefficient. What are the dimensions of this physical quantity? First of all, two quantities are added, so dimensions of A and dimensions of B, they must be the same. And so dimensions of A and dimensions of B, they are expressed in terms of some single expression. So suppose that it is dimensions of length to the alpha, mass to the beta, and time to the gamma. Because it is nth power, so if the dimension is fixed like this. Compute the binomial coefficient nk. This is supposed to be the same as the number of cases. If you choose A and B by n times, the sum of these two indices must be the same as n. How many distinguishable cases are there? That's the problem. First, we consider a very simple case. A plus b squared, we can expand this expression. So it is a squared, AA, AB, and BA, and BB. We make use of commutative law of multiplication of two numbers, then it becomes the same. So we have twice A times B. So AA is expressed as A squared, and multiplicity of choosing A twice is only a single time. The multiplicities of choosing A once and B once are 2. And choosing B twice is a single case. The coefficients 1, 2, 1, 2, and 1 are interpreted as follows. 1 in front of A squared is the number of cases of choosing A in every factor. We have two factors. In the first factor, choosing A. In the second factor, choosing A. And discard B in both cases. The factor 1 in front of B squared can be calculated in an identical way as we have used to compute the coefficient in front of A squared. The factor of 2 in front of A times B is the number of cases choosing A and B one by one. Here choose A, here choose B, and we choose B in the front factor, and then choose A in the next factor. Next, we consider the case we have n factors, n identical vectors. So a plus b times a plus b times by n times. We would like to denote the factor in front of a to the k and b to the n minus k to be this. And this is binomial coefficient. We'd like to determine the expression for this binomial coefficient. Sum of A and sum of A's power and B's power must be n because there are n factors. If I choose A in a single factor, then I don't choose B. So number of cases should be either 0 or 1. Choose or not to choose. If I choose A, then I have to choose B. This choosing A, yes, no. Choosing B, if it is yes, it should be no. If it is no, should be yes. Yes. So the answer is actually n factorial divided by k factorial divided by n minus k factorial. The reason is that I have a 1 through an. If they are all distinct, then number of permutations. That means I choose 1, 2, 2n, or n minus 1, 2, 1, something like that. Listing n distinct number in order should be first I choose one of them, so I can choose n elements. If I have chosen a single element, then I'm left with n minus 1 elements. Then I can choose n minus 1 of them. And once I choose another element, the remaining elements are n minus 2. In such a manner, I end up with the last element, and then there's no other case. So this is called n factorial. If I choose n distinct elements in order, so this is called the number of permutation. However, I have chosen n factors, but among n factors, there are Ka's, there are n minus KB's. If they are all distinct, this is true. However, I have same factors A by K times. So I have double counted the permutation of these A's. Suppose that I have A. How many cases can I have to choose A 3 times? Only a single. There is no way to distinguish the exchanged one. If I exchange A and A, then I still have A. So they are the same. It is indistinguishable. But what I have done is I suppose I have distinguished all of KAs. So I have made a mistake. I have treated them all distinguishable. However, in fact, they are not distinguishable. Therefore, I have to divide this one by k factorial. The same is true for the case of choosing b's, and there are n minus k b's. They are not distinguishable. Therefore, I must divide this vector by n minus k factorial. This is the number of distinguishable cases to choose k times a and n minus k times b, and the sum is n. So n factorial divided by n k factorial n minus k factorial is the binomial coefficient. We compute the derivative of 1 plus x alpha with respect to x. We find the derivative of log first. We know derivative of exponential function is the same. So we substitute y for the e to the x, then this differential equation is dy dy over dx equals y. So we can rewrite this one. Separation of variable, divide both sides. So we multiply dx over y both sides. Then y cancels, dx cancels. I obtain this. If I attach integral notation, this is trivial integral. I have neglected the integration constant that is arbitrary. Now, we return to the replacement y equals x to the e to the x. That is identical to x equals natural log of y. So I have replaced x with log y. Therefore, we have constructed integral table for dy over y. It is log y. Again, if we take the derivative of both sides with respect to y, then we return to the original one. That is the integrand, 1 over y. Because e to the x is y, we substitute, we take the power of alpha. The law of exponent shows e to the x alpha is just a product. This is a product. Power is the resultant power is the product. And y to the alpha. We make use of the inverse transformation. Y equal e to the x is x equal log y. So this is power. Power should be alpha log y. That is the same as log alpha to the y to the alpha. We know this because x equals log y. Therefore, this identity should go in this manner, and I use this to replace x alpha to be alpha log y. So we have concluded that log y to the alpha, this power comes out of the log as a linear form. As a result, if I take the derivative of log 1 plus x to the alpha, because the power can always be pulled out in front of the log, and this alpha is a constant, so I can move this alpha out of the derivative. Now we take the derivative of log by making use of chain rule. This function of 1 plus x, I first take the derivative with respect to 1 plus x, and then take the derivative of 1 plus x with respect to x. And that is trivial. So this is 1. And this is log 1 plus x. This is log 1 plus x. Derivative is log's derivative 1 over something. So 1 over 1 plus x. As a result, you should remove this period. Then alpha divided by 1 plus x. So find the derivative of 1 plus x to the alpha for all x satisfying. 1 plus x is greater than 0. Okay, so we need to restrict x region to have the log to be defined. So this should be positive. Sure, later, if you can extend the region to the complex number, but it is out of the scope of our class. X to the alpha. Anything positive should be e to the log. because e and log, they are inverse function. So this e to the log something should be something, identical operation. We know log something's power is that power is in front and log something. So I can rewrite this one as e to the alpha log. Now a1 plus x to the alpha because of the identity operation, and then the power exponent comes out. So we have exponential alpha log 1 plus x. It is identical to each other as long as 1 plus x is positive. Let us compute the derivative. Because we know how to take the derivative, this is trivial. Now we substitute in here and this one and then this. Now we make use of the derivative. This is exponential. So chain rule. Exponential something, take the derivative with respect to something. This is the same. However, we take the derivative with respect to x, we need to use the chain rule. So the result is this one multiplied by the derivative of the argument. So argument is this. And we know the derivative of log, that is 1 over something. So alpha 1 minus x. We return to the original definition of this. This is nothing but 1 plus x to the alpha. Therefore, we can divide this 1 plus x in here. As a result, over a factor alpha appears and 1 plus x cancel, so this power decreases into alpha minus 1.